Have you ever stopped to wonder what makes something like glue, well, sticky, or why honey is so thick, but water just flows everywhere? The secret, it turns out, isn't really about what molecules are made of, but how they're shaped. Today, we're going to pull back the curtain and see how a molecule's invisible 3D structure is basically the master architect for how it behaves in the real world. And really, that brings us to the central puzzle we're trying to solve. Why are some things so clingy? It all boils down to this one simple question. Why do some molecules stick to each other like magnets, while others just seem to want their own space?
All right, take a look at this. We've got 3 different molecules here: propane, propanone, and 1-propanol. They're all roughly the same size, same weight. But check out their heat of vaporization. That's just a fancy term for how much energy it takes to rip them apart from a liquid into a gas. Look at that difference. It takes more than double the energy for 1-propanol than for propane. So what on earth is going on? Well, stick with me because by the end of this, you're going to know exactly why.
To solve this mystery, we have to think like molecular architects. And every architect needs a blueprint, right? In chemistry, our blueprint is something called a Lewis diagram. So what is a Lewis diagram? It's basically a simple 2D sketch. Think of it like a flat map that shows us exactly which atoms are connected to what, and most importantly, where all the outer electrons are hanging out. The electrons that are doing all the interesting work. This simple map is the foundation for absolutely everything that comes next. And don't let their simplicity fool you. These little diagrams can reveal some really deep truths. Let's look at nitrite and nitrate. Their Lewis structures show us that the electrons aren't just stuck between 2 atoms. They're actually spread out across the whole molecule. It's a cool concept called resonance. This means the bonds aren't really single or double. They're somewhere in between. In nitrite, they're like 1.5 bonds. In nitrate, more like 1 1/3 bonds. Just think of it like a rope. A thicker rope is stronger, and it's also shorter. That higher bond number in nitrite means its bonds are physically shorter, which is a real-world property we figured out just from our 2D plan. Okay, so we've got our 2D blueprint. Now it's time to actually build the 3D model. And to do that, we get to use this incredibly simple but super powerful rule called VSEPR theory. Yeah, I know, VSEPR, valence shell electron pair repulsion. It's a mouthful, but the idea behind it is so intuitive. See, electrons are all negatively charged, so they just can't stand being near each other. They will literally push and shove to get as far apart as they possibly can. And it's this constant pushing that forces a molecule into its final unique 3D shape. Now, this is a perfect example of VSEPR in action. Just look at the difference between ethene and ethane. Ethene has that double bond, which creates 3 zones of electrons around each carbon. So, to spread out, they all lie flat in a shape we call trigonal planar. But ethane, it only has single bonds, so that's 4 electron zones. The only way for them to get far apart is to pop out into a 3D tetrahedral shape. So one tiny little difference in a bond, and boom, a totally different geometry. Okay, so VSEPR theory tells us what shape a molecule makes, but it doesn't really tell us how. How can an atom like carbon, with its very specific set of orbitals, even form those shapes in the first place? Well, the secret is a wild little concept called hybridization. Just like Jeremy Krug says here, atoms can actually take their existing orbitals and, well, mix them together. They create brand new hybrid orbitals that are just perfect for making certain bonds. The best analogy I've heard is mixing half a glass of milk with half a glass of orange juice. And yeah, I know that sounds absolutely disgusting. But for atoms, this mixing process, hybridization, is the magic trick they use to form strong, stable bonds in all these different shapes. Now, you might be thinking this is going to involve some crazy complex diagrams, but for AP Chem, you're in luck. There's this fantastic shortcut. All you have to do is look at the central atom and count 2 things. First, how many sigma bonds does it have? A sigma bond is just the first connection to any other atom. So a single, double, or triple bond, they each count as 1 sigma bond. Second, count the lone pairs of electrons on that central atom. Then you just add those 2 numbers together. That's it. And that number you just calculated, that number is everything. You just look it up on this handy little chart here. If your sum is 2, the hybridization is SP. If it's 3, it's SP2. If it's 4, it's SP3. It's really that easy. This table is your key. All right, let's put it to the test with propyne. Let's look at that first carbon atom in the triple bond. It's connected to a carbon on the left, that's one sigma bond, and it's connected to the carbon on the right with that triple bond. That's our second sigma bond. So 2 sigma bonds. Any lone pairs? Nope, 0. 2 plus 0 is 2. We look at our table. A sum of 2 means its hybridization is sp. See? Simple. Okay, so let's recap. We have the 2D blueprint, we have the 3D shape, and now we even know the reason for that shape. With all that, we can finally figure out the molecule's overall character. We can ask, is the electron charge spread out evenly, or is it kind of lopsided? This whole idea is called polarity. Really, it all comes down to one word: symmetry. In some bonds, one atom pulls electrons a little harder than the other, creating a tiny electrical pull. Now, if the molecule shape is perfectly symmetrical, all these little pulls cancel each other out. It's like a perfectly balanced game of tug of war. That makes the molecule nonpolar. But if the shape is wonky or asymmetrical, the poles don't cancel. You're left with one side that's a little negative and one side that's a little positive. And that's a polar molecule. Let's look at our poster child for a nonpolar molecule, carbon tetrafluoride, or CF4. It has this perfect symmetrical tetrahedral shape. And even though each of those carbon-fluorine bonds is pulling really hard, they're all pointed in perfectly opposite directions. They completely cancel each other out. The end result? No overall pull. It's totally nonpolar. But now, check out sulfur tetrafluoride, SF4. It's also got 4 fluorine atoms, but it has a secret weapon, a lone pair of electrons on the central sulfur. And that lone pair acts like an invisible bully, shoving all the bonds out of whack and creating this weird, asymmetrical seesaw shape. Because everything is lopsided now, those poles don't cancel out. The molecule is left with an overall pull, making it polar. And here we go. This is the moment we've been building towards, the final payoff. We've gone from a 2D drawing to a 3D shape to a molecule's character. Now we can finally connect all the dots and solve that original puzzle about our sticky molecules. Remember this table from the beginning? Propane, propanone, 1-propanol. 3 molecules all about the same size, but with these wildly different heats of vaporization. So why? Why does it take so much more energy to pull 1-propanol molecules away from each other? This chart just makes it so clear, doesn't it? The energy needed for 1-propanol is just massive compared to propane. And here's the key. The reason for this huge gap isn't about the bonds inside the molecules, but the forces between them. And those forces are a direct result of everything we've just talked about, shape and polarity. So here it is, the final answer. Propane is nonpolar, so the only thing holding it together are these super weak, temporary forces called London dispersion forces. Easy to break. Propanone, though, is polar, so it can use stronger dipole-dipole attractions to stick together. But 1-propanol, it's the special one. It's polar, and it has a hydrogen atom bonded directly to an oxygen. That allows it to form something called hydrogen bonds, which are basically the superglue of intermolecular forces. They're incredibly strong, and that's why 1-propanol is so sticky and so hard to pull apart. So there you have it. We solved the puzzle. The invisible architecture of a molecule directly determines its personality in the real world. And that just leaves us with one final thought to chew on. What else in the world around you, from the way a flower smells to how a medicine works, is secretly being controlled by a molecule's hidden 3D shape?